I'd like to thank the organizers who invited me to this extremely informative workshop and learn quite a bit things, new development. So I'm going to tell you about the recent development of the 2D superconductivities, especially that related with the twist layer Moiré carbon the superconductivities. I'm trying to address that superfluid stiffness measurement using the reflectometry, and that the most of the work is in the archive papers about 2 months ago. There's actually quite similar work they posted about the same time. The Moiré was group at MIT. Okay, so let me start with the acknowledged people that who did this work. Abhishek Banerjee is a postdoc of my group, and Jae Hao is a graduate student, graduating graduate student. Two of them are actually the main people actually push these experiments together with very strong collaboration with the Casey Fong's group. Casey provide a lot of this RF technologies. Some samples coming from the MIT Pavlo's group, as well as a kind of theory that many of them, except Pavel, I'm seeing all of them sitting somewhere in this room. And as usual, HBN coming from Japan. So when we discuss about any superconductivity that you want kind of being asked to demonstrate, all right, that zero resistivity and the Meissner effect, of course, in the 2D materials, and especially this small scale of this Moiré superconductivity, often that diamagnetism is rather difficult to demonstrate, but there is some of the related things one can study about. It turns out that simply that if I just kind of write the gauge, this London equations can kind of explain both of this phenomena at once, and this at the London gauge that the proportional coefficient between that current and the vector potential is often what we call this superfluid stiffness. And obviously that is a very important quantity, in some sense thermodynamic quantity, as we mentioned a couple of times throughout this the workshop. It's kind of one of the important governing quantity for the superconductivity we all want kind of know about. By the way, the name superfluid stiffness, I got confused a little bit because I haven't studied about superfluid helium. Obviously, that comes from the superfluid communities in general, including the superconductivities. The superfluid stiffness is defined as the coefficient kind of connected with the free energies with the change of this superfluid, the order parameter phase changes, and there comes the name comes from it. But important part is that any of the superfluidity, the superfluid density divided by the constituent mass is proportional to this stiffness, and that becomes quite important. In fact, in that definition, this superfluid stiffness as units of the energy. Often that the units of this one we'll just kind of discuss later a little bit. Anyway, because this is important quantity, there are many ways that you can address and measure it, and often that measurement is either static or dynamic response of the magnetic property of the system. Either you can stick into the microwave cavities to measure some of single crystal superconductor superfluid stiffness, or if it's thin film, that you can just use as a mutual inductance type of the measurement. You can address that magnetic shielding to get this information about the magnetic shielding length, or that the penetration length scale, which actually is directly related with the superfluid stiffness we are talking about. Both of this type of the approaches are a little bit difficult, especially if the sample size is small and the sample volume is small. And sometimes this size kind of some of the issues, so you need kind of special technique to measure it, and that's what I'm going to kind of present kind of later on. The whole purpose of this, the work, in some sense, is that we want to kind of show that whether the superconductivity we observe in the Moiré graphene system is indeed unusual superconductivities, right? So when you say the unusual superconductivity, of course, unusual superconductivity often comes with unusual phase diagram. Probably the most unusual superconductivity we know about cuprate has this complicated phase diagram, but in some sense, there is this the broken symmetry state, the antiferromagnetic states, and doping this antiferromagnetic insulator that create this superconductor, competing with all this the competing or the cooperating the broken symmetry states is kind of something that define this phase space. from the very beginning of this field, that when Pablo showed this nice phase diagram of this the twisted magic angle twist bilayer graphene superconductivity, this phase diagram has at least analogies with the Q plate we can see, right? There is some insulating state, doping the insulating at the superconductors, and there are some of this broken symmetries got involved. I think that in terms of kind of sheer analogy, it seems like there's kind of something that are connecting and indicating something unusual. But is this really kind of really unusual? That can we quantify? It becomes clear that although it's interesting, in the very first paper, it was marked as a MOT, but now we don't call this MOT because we now know that a couple of times that mentioned throughout this the workshop is all these kind of broken symmetry states actually sometimes has a topological, and there's kind of turns out this many of the insulating states, which is a model of this superconducting state, is in fact a topological. There's kind of often the Chern numbers or valley Chern number can be associated with it, which is kind of marked difference between the Q plate physics in some sense, right? And what I'm going to discuss today is mostly just kind of focus on the twist, the graphene, Moiré, the superconductivity, especially the related with this multi-layer, the Moiré system, including twisted bilayer, magic angle, tri-layer, 4-layer, 5-layer. That's kind of only the topic, but even that topic, there's something commonality we can just get it, right? When it tunes with the sharply tuning this magic angle, that you can get this kind of extremely flat band. And once you're away from the twist bilayer, often that is combined with some of the so-called the dispersive band kind of together. And often that in the tri-layer, 4-layer, 5 layers, displacement field, as we heard, plays an important role because that can hybridize with this flat band. You can modulate the band structures by the displacement field. So often that displacement field is an important tool that also in the single particle level that can tune around these band structures, which give us some of the additional knobs there. In fact, using this knob, that we can actually quantify that kind of following argument. Is this really superconductivity is related with broken symmetry states? Some of the recent work, and has been claimed and shown that a little bit, but some of the recent development that we show here is a 4-layer graphene displacement field and the fielding. You can see that this is subtracted, normalized the Hall coefficient, where that you can roughly see that what is broken symmetry states numbers, degeneracy number. And here is so-called this nu equal 2 broken symmetry states appears, doped broken 2 symmetries. That appears as the phase boundary of the broken symmetry state. Note that not only fielding in the displacement field, eventually this broken state go back to just single particle, the normal the states changing its number from the 2 to 4 and degeneracy number. And that's because that as you increase the displacement field, eventually flat bands start to hybridize and basically the bandwidth becomes larger and mixed together and becomes kind of normal band. And that's kind of usually seen this the Hall measurement. What you notice that is that this broken symmetry state 2 is kind of precisely aligned with when you just measure the vanilla plane conductivity and show the superconducting state. This where the superconducting state appears here is more or less matched with this broken symmetry state 2. You can do a little bit more careful work and cut it through and precisely show that when broken symmetry state is gone, superconductivity is gone, right? So the first kind of rather interesting, and the statement one can make is indeed, at least it seems like that this twisted layer, the superconductivity is related with this broken symmetry state. And then whenever broken symmetry state is there, it seems like superconductivity exists. That's already give you a little bit of a hint that might be some of the unusualities comes in. Over the past few years, there are quite of the experimental evidences that are kind of piling up that indicating the potentially superconductivity unusual. Kind of depends on what your definition of the unusual. For example, there is the report of the nemestis of the critical currents probed by the in-plane magnetic field, the Pablo's group a few years ago. The Pauli limit violations, especially with in-plane magnetic field, and usual violation go for the 2, 4, even we heard about 20 or 8, quite big numbers, right? And scanning tunneling spectroscopies, including the previous speakers, show that often that when you measure STS, the gap is rather soft rather than kind of hard gap, and indicating there might be in-gap excitations or kind of hinted this gapless superconductivities, I think, or nodal superconductivity. I think that's kind of some of the evidences. Reasonably indirect, but that kind of quite suggestive. Quite recently, this is the measurement done in the Ginny Lau and Mark Bocarath group at OSU. And what they measured is, it was a slightly indirect, but they measured basically how the critical current behave, either non-superconducting, superconducting states. And from that critical current behavior, they can infer, it's rather indirectly, that zero temperature superfluid stiffness. And what they see that is that zero temperature superfluid stiffness is fairly large. I mean, especially compared with what you just kind of expect, simply that parabolic band with this, the massive renormalizations, that they actually have the order of magnitude larger superfluid stiffness. Again, that can be hinted, this going for the, this unusual superconductivity. Right. What I'm going to tell you today is how we can just kind of look at this kind of slightly different pictures. So again, I think this is a picture that I just took out from Pablo's original paper. And then this paper, the purpose is basically look at the gap that measured, or gap that inferred with the Fermi level inferred, usually go for the TC over the TF, and plotting in this diagram where the twisted bilateral graphene. That is a push toward more of this, the left upper corner, which is usually considered as a strongly coupled superconductivity, unusual side of that. With this large pair of these things. This is not the first time it's just put up there. This is what usually called the Uemura plot, and starting from the cuprate, right? And kind of try to put this one, and cuprate is indeed compared with the conventional superconductor. Go close to the where T of the TC over the TF is very large, right side. I think that's a kind of, again, another the empirical indication of the unusual superconductivity. But you may say that how do our TC can be measured, but how to measure TF on here? What is the meaning of this one? In fact, the way that Uemura plot is plotted here is not just estimating and measuring the Fermi energies. It is, in fact, they're coming from superfluid stiffness measurement. So where that this one is measured from the penetration length measurement, and because superfluid stiffness is related with N over M, which is basically the basic ingredient of the Fermi energies, it was kind of plotted in this way, right? So maybe we can ask that, kind of containing all of this thing, can you just measure superfluid stiffness in this the Moiré superconductors, and just put this kind of plots in some way. So that's kind of the directions I'm going to kind of push along. Another, the unusual superconductivities, the signature is also the measuring the pairing symmetry, was kind of discussed already, and measuring pairing symmetry using the various the interferometry method. In fact, is one way that pin down d waveness of the superconductor. It's a little bit hard in this 2D superconductor in general, not only just Moiré superconductivity, because magnetic penetration length is long. So controlling this into the sum of this squeeze type of the device corner junction and those kind of things does not work too well compared with this 3D superconductor. However, at least when you have this nodalist and versus nodal superconductor, there's one thing that important that you expect when you go to finite temperature. At finite temperature, when you have this nodal superconductor, there is always some sort of quasi-particle expected at any finite temperature, right? Therefore, if you just measure any quantity such as superfluid stiffness, indeed the temperature dependence of the superfluid stiffness will tell you about that, how this the nodal versus nodalness comes from just looking at the temperature dependence of the measurement. So that's basically all the motivation. So how do you measure? Well, so because it's a small sample, there's kind of most of the other conventional way of the measuring superfluid stiffness doesn't work too well. But there's one way that we can address this by simply measuring so-called kinetic inductance. Kinetic inductance is nothing but when you send the current through, that all the carriers kind of flowing through, they will have the kinetic energies. If you just write down what is the kinetic energy of the carriers, simply you can just rewrite down in terms of, time is up already. In terms of the current square and the coefficient, which actually is nicely kind of tucked into the inductance units. This basically consists of how many carriers I have, how heavy is the carrier, and those kind of things. Because of this is an inductance unit, we can call this is often kinetic inductance. Not only is the inductance unit, in fact, if you just put into the circuits in there, it behaves like the inductor. Therefore, that we can, in principle, measure the inductance response of any conductors. We can just measure it in principle. However, to get this is appreciable inductance response compared with the geometrical inductance, you need kind of really, really thin sample. So 2D sample is ideal, but also you don't want to have the sample resistance in there, which actually compete with the inductance. So it only works well when you get into superconductors and just doing this measurement. In fact, it is another kind of new concept. It has been already studied into that. It can be even used as a really practical device as a detector. Already astrophysicists kind of make that this superconducting kinetic inductance detector, send it out the outer space probe, and kind of they really kind of fairly the standard the tools now. All right. So a few more things about the kinetic inductance. What we need to do is kinetic inductance is related with the superfluid stiffness, as I mentioned, right? But that's only when you just kind of do the so-called sheet kinetic inductance, which require the sample dimensions. And you will see that why actually I emphasize this one in a moment, right? And as I said, the kinetic inductance and then the superfluid stiffness is related with kind of linearly with some kind of well-defined constant there. So in principle, the kinetic the superfluid stiffness, as I mentioned, is the energy unit. If I divide by the Kelvin, that it's the Boltzmann constant, it can be used as a temperature as a unit, which is quite convenient sometimes. Or I can just express this in terms of the inductance unit, Henry inverse. So you will see that throughout talk that I will just use one unit versus the other one. Important signatures I want to kind of look at here is first whether it's a nodal or nodaless superconductor. And as I said, that can be just the measure throughout this temperature dependence of the kinetic inductance measurement to convert into the superfluid stiffness. Whenever any nodal superconductor, doesn't matter P or D or F, right? As long as there's node, as you increase the temperature, you start to see that kinetic inductance, where it's kind of, or the superfluid stiffness decrease quite rapidly because you have the quasi-periodic excitations out of the superfluid condensation, and you expect to see the N sub S actually decrease. And that's the reason that I expect to see that this kind of steep decrease of the superfluid stiffness. So that's kind of something that I want to see. Compare with rather the slow decay. In fact, it's activating decay of the superfluid stiffness when you have this nodaless, yes, as a gapped superconductors. I think that's the part. The way that we just do the experiment is that to measure inductance, the response of the sample. Therefore, that we have to go for the higher frequency. We are using about the radio frequency to the microwave ranges, 100 megahertz, gigahertz range of this the frequency dependence into the measurement. To send out this sample, to send out this radio wave and get the reflectance out, and that contains information. For that, we have to build up the matching circuits to match that deliver the microwave powers into the sample in the right amount, and that has been kind of done. But in the end of the day, that we just kind of measure the inductive response of the sample. So what does it look like? So this is kind of how the data look like. So here is twisted tri-layer graphene, typical DC transport sample. So we can just first do the DC transport measurement and just look at the resistance changes as a function of the gate voltage, which I already converted into the filling fraction of the Moiré. And what you see here is that between 2 and 3, negative 2 and 3, and one bit around the 2, we have the superconducting regime. Hole-like the regimes and electron-like the superconducting regime is nicely showing up with something than in the DC transport. Now, what we can do with that is, with the same device, now we just kind of send the RF in, kind of remove the DC connection. We just can put the RF, the radio frequency in, radio waves out, right? And just kind of look at how the reflectance of the sample look like. And as I said, we just kind of put this matching circuits in there to deliver the right amount of matching powers in the frequencies in there. And when you just look at this reflectance of these signals, first thing that if we simply compare with the superconducting versus non-superconducting regime, the first thing you see that is there is a shift of this resonant frequencies. And if you just kind of go through this lump circuit elements analysis, that resonance frequency is related with this kinetic inductance. And that's basically, and while everything else is kind of fixed, basically I can just kind of extract the information out of this kinetic inductance changes simply just looking at the resonance frequency shift. Of course, we can just do that with not only these two different gate voltages continuously sweep through and just look at the reflectance measurement. This reflectance, this dark blue region is where the peak is kind of changing. So you can see that peak is continuously moving around as I'm just going through superconducting normal to the superconducting regime. And you can see that clearly the shift of this resonance frequency can be connected back to the change of the kinetic inductance of the sample. Now, you have to do a little bit more careful work. It's not only shift, but you can see that there's a Q factor that changes, all these things got changes simply because it's not simply inductance response, but it is a network of the response of the lump elements. You have to go through the a little bit careful analysis, both amplitude and phase, and the shift of the frequencies are kind of needed. But at the end of the day, that you can just extract the kinetic inductance of the change of the sample. So that's kind of point out of this one through all these gate voltages. However, I should point out, once that sample is away from the superconducting region, so as you approach the TC where the sample starts to develop the resistance, right? This analysis becomes rather too simple, and then you start to kind of see that so-called the device is more of the inductivity driven, and where that extraction of the kinetic inductance is not as believable. So there is a region that I have to cut it off. That's the region where the resistance of the channel starts increasing. Basically, I start kind of stop to believe that this is really kinetic inductance of the sample. But nevertheless, deep inside of the superconducting region, in the lower temperature, this is a kind of rather accurate kind of estimate the kinetic inductance. Okay. With this kinetic inductance, let me just convert that into the superfluid stiffness and just look at how this look like. So I'm showing you that some are different gate voltages that we just kind of cut off the superfluid stiffness as a function of temperature. We just already cut it out, something that I cannot trust anymore of this value. The first thing that you notice that here is that, all right, the kinetic inductance as you change it from the lowest temperature, which is about kind of the 100 millikelvin-ish and above, that everything's kind of linearly dropping down, right? So at least just looking at this one, this kind of clearly shows that across the dome that I'm seeing the superconductivity. Superconductivity seems like the node has nodal superconductivity. Second part is, if I just look at this, the zero temperature value or the zero temperature extrapolation of this superfluid stiffness, there is kind of large variation as I'm changing the gate voltages. So let me show you that how that changes. So this is a zero temperature or zero temperature limits of the superfluid stiffness as a function of nu. It actually do changes across this dome, right? In fact, we learned that we see that this the change is very much kind of correlated with this TC that we measure from the transport measurement. Although it is a different scale, but you see that there's a peaks of the dome, that there's a peak of the superfluid stiffness, and they kind of do changes quite faithfully. The other thing you notice that is that the slope also do changes across this dome, right? So let me just kind of take the slope of the d rho dt and just plot it out in terms of nu, and this is kind of how the slope changes, right? So you see that if I see that this is dome and this is the hole side and this is electron side, and I can see that there is the slope is kind of more stiffly vary here, that there is a big jump across the optimally doped region and more like the constant electron side or hole side. Yeah. So there is electron side. So there is some of these changes. So the first task here is, can we understand how this behave? Why the TC is correlated with this, right? So this is kind of first thing that we want to explain. Luckily that, if you just go through that, when it goes with the nodal superconductivities, already D-wave superconductor has been kind of out there for almost kind of close half centuries now, 40 years, yeah. So there are a lot of kind of the theory works there quite early on, so we can just kind of take some of the theory work that how that when you have the nodal superconductivity, how the temperature behavior of this superfluid stiffness changes, and you can just extract this. One of the original paper by Patrick Lee and the Shagan Wan's papers just kind of look at that, and that is how that superfluid stiffness changes as a function of temperature. Main ingredient is how that this the band structures, the energy changes, which will give you the effective mass of the system. And this is the part coming from the temperature dependence part, and the zero temperature part is the temperature dependence part, which express in a sense how that the quasi-particle is excited across this Bogoliubov dispersion relation we expect for this northern superconductor. It's actually governed by Vf with V delta. V delta is nothing but this speed of this Bogoliubov quasi-particles in this dispersions, right? So since we have these equations, in some sense, we can just first qualitatively explain that whether we can explain this behavior. The first thing that we can see that is that if I just assume any band, let's say that I just address straight out that Hartree-Fock band for the broken symmetry state n equal 2, that is a model state I can start with. We all learned that from this paper where that most of the authors in this audience, that the band structures or the Hartree band structure is something like this. It's heavier into the electron side and the lighter in the hole side or something like this, right? But just looking at this type of, this is my band structures I can plug in there, more or less explain this behavior, right? Because you can see that here that is a hole-like turn into electron-like, and that mass becomes kind of infinite at some point. And when mass becomes infinite, I just banish this one. And from there on, that carrier sign changes. Therefore, I start kind of bringing it up. Nk here, that Nk drops. And more like that, this one is explained by, again, just looking at the zero temperature behavior with this is my just a dispersion relation of the band, right? Second part of this one also can be explained. The d rho dt can be explained because this is nothing but related with this ratio between Vf of V delta. Let's assume for now V delta is constant. Then basically how the Fermi velocity, which is the slope of this one, is got changes. I can explain it. In a sense that you can see that whole side of the slope is larger than the electron side. Therefore, that I can see that roughly that the at least qualitative way that we can explain kind of how this can behave as long as I assume this one. So at least we can just do this qualitative fashion, so we can do that. However, we can go more of the quantitative expressions later. But nevertheless, already, this one, indeed, if that is the case, right, simply just look at this. Other than the temperature dependence, other than this ratio, all other thing is basically kind of known quantity, right? So I can convert the d rho dt, which is these things, exactly convert into the what do we expect the Vf of the V delta if I just look at this novel superconductor. Turns out that Vf of the V delta is about 10 times, right? So the V delta is about 10 times smaller than Vf. That's basically immediate conclusions we can get out of this the measurement. Since I claim that I measure the superfluid stiffness in all temperature, in all the density that measurable, you can attempt to do the following things. So this is, by the way, data. So that rho s is a function of the temperature and the density. You see that kind of all this curve. See, if you just do this one, in principle, you can just do also calculate the BKT transition temperature out of it, right? Because the BKT transition temperature is defined by the where that rho of the T is equal to this linearly transport part. Just looking at plain cut of this data, I can get this what is BKT transition temperature. But then, when we just plotted out this BKT transition temperature, we have some problems we found. So BKT transition temperature that we have here is the blue curves, which is more or less reasonably correlated with this the superfluid stiffness we measured. But it's actually about 3 times, or very much suppressed compared with the TC that we measured from the transport. What does that mean here is, at least if I just follow through this, above the BKT transition temperature I estimate from the superfluid stiffness measurement, I have still zero resistance state, which doesn't make sense, right? BKT transition temperature is where the vortex start to unbound, they start to dissipate it, so it doesn't kind of make sense. We scratch our head, and then we found that indeed there is a kind of interesting correlation between the TC that we measure and BKT transition temperature. We just kind of look at that in terms of the same as the density changes, put them together. they are kind of nicely linearly lines up with over the factor of the 3. Right. So in a sense, our TC is of a factor of 3, larger than BKT transition temperature measured in this way. So one way we get around this the thing is indeed the sample that we are measuring, as we all know, is not necessarily really clean sample. There's always twist angle disorder in there, right? So yes. TC is basically transport measurement at the foot of the transport the rising, which usually, if you measure the ID characteristic, identify as a BKT transition temperature from the transport. Yeah. So this TC is basically this BKT from transport. You can just kind of put it this way. Rise from 0. Yes. Yeah. That has been kind of measured many times. So the way we can avoid it, this idea is indeed, if you just look at the experimental rho S estimation, I just mentioned that I have to put the sample geometry, length and the width, right? What if the sample is a disorder, right? And our superconductivity measurement that we are doing, including this RF measurement, in a sense, it is still kind of measuring filamentry across the sample, right? If it is a kind of filamentry of the superconducting regime that by the population, then what I expect to see that is indeed that this can be rescaled, right? A rescaling factor that if I just put a 3, that I can just kind of resolve these issues, right? Okay. So that's kind of the one thing. And one thing, once you include that one, and if I just restore back to whatever this Uemura plot, I get the kind of really nice the Uemura plot with its kind of one sample sweeping through the density, right? And then if you just look at this this TC over the EF or the TC of this row, then you get about 10%, which actually is again kind of indicating very strongly the correlated system. If I just kind of repeat this through the many other samples, more or less they are kind of scattered, but more or less the slope stays kind of very similar way. All right, so Andrea is up, so which means I don't have the time to go through the other part, but you can just repeat this with in the presence of the current, so-called the nonlinear the Meissner effect measurement, which is another way that you can extract these nodalities. Not sure is you can get all these kind of things that do the measurement. An important part is that we can using this nonlinear the measurement, you can extract information about both the VF and V delta separately, which is again something like the reasonable ranges that you can see there. Okay, so as a summary, that before close down, kind of one the open questions I want kind of ask. That is kind of absolute magnitude of this measurement that we have, right? So I mentioned that we have the superfluid stiffness, and now I just convert in terms of Henry about this ranges. In fact, that is kind of comparable ranges of the all other measurement, including the MIT measurement I mentioned. It's about the same orders, right? Now this magnitude is kind of much larger than what is expected from just kind of put the effective mass of heavy mass in there computed. It's about order of magnitude larger. Now I mentioned this Hartree-Fock band things, right? If you just go to the Hartree-Fock band estimation and put up there, the Hartree-Fock band estimation give you about 10 times larger than measured the superfluid stiffness. So experimentally accessed superfluid stiffness is somewhere in between. I believe that that is probably two bound we can just put up there. And what I was told from the theorist is this is where that indeed quantum geometric consideration is important, and to compute that what is a superfluid stiffness on this twisted graphene system. So there's room for the theorist that this is a question that your task. Now, upper bound and lower bound is there. Just get these numbers. Thank you.
Lots of questions. I'll start over here and work my way over.
Wonderful stuff. I have one small comment and then a real question. So the formula that you use to extract VF over V delta, that assumes a certain number of nodes, right? The leave-in story is for D-wave superconductor with 4 nodes.
Yeah.
Now here it may be P-wave. It may have there may be a factor of 2 difference.
Yeah, that's right. You're exactly correct. There is the number of the nodes should be in there.
Should be in there.
I think that we put the 2 rather than 4. But yes.
But since you say you can extract VF and V delta separately, but sure with some error, but probably not a factor of 2 error.
Yeah, that's a kind of really, first of all, you can see that there's a log scale there, and there's a reason that we put the log scale. Factor of 2 is easily hidden here. But yes, indeed, I think you should not trust this one too much. I think if you just look at this, the arrow bars there, estimation, that's easily factor of the 2.
Oh, I see.
There.
Okay.
Right. But at this point, I'm not claiming this is a really precise kind of number we put up there. I think this is a reasonable number we can believe about order of magnitude.
Okay. So the main question was, can you measure this as a function of displacement field as well?
Yes, I think that's kind of the part. I think as Stefan, if he's still around, right? You can send us a sample. We can measure tomorrow. Oh, yeah. Because I think this measurement requires basically not a special consideration, except that we can just put the matchings onto the right next to your device. Not necessarily need to be on the same chip. So within kind of our sample packages, I can consider lump elements. I can just do that. And that's why that it's nice that work on the 100 megahertz to gigahertz ranges. You don't necessarily need to, everything's kind of on-chip matching. So that's kind of the nice part. Other than that, all the measurement that we are just doing is some of the device that we just did a DC transport measurement, plug into this RF setup and just measure it. So in principle, it can be done. In fact, we had this, here that some of the sample that we got it from Pablo's, the DC measure sample, just plug in there and just in there. So I think that worked it out.
Is that velocity that you showed relative to just graphene?
No, I think this VF is a VF also we estimated. So that is a band velocities. That,
the scale relative.
Yes, yeah.
Smaller?
It is smaller. It's about the factor of order of magnitude smaller, I think. Yeah, I think that, let's see that. So it's about, actually, right, so this is about the 10th, well, even the 2 order of magnitude, it depends on the factor of the 20 smaller, right, yeah.
So you said that there's some evidence that the superconductor is disordered. So how can you distinguish nodal from disordered?
Yes, okay, that's a very good point. Yes, yeah, that's a good point. Raquel, you haven't worked on to the cuprate, how come? You ask that question. Usually that is I expected from the JED ask similar questions. Okay, that's a kind of valid point, right? I think I would say this omega star things that I just put up there to boost this the superfluid stiffness to match with this DC transport BKT is a fuzzy factors. Other than that, I don't have yet in this experiment that whether this is really justifiable and things. It's a reasonable number that I can expect, but it's not justifiable within the experiments. However, barring that part, the temperature dependence linear part, I don't think that is affected by the disorder too much in the following sense. Usually you can just make this linear slope and put the disorder, you can smush that out, it's less linear. I think that's kind of a huge issue of the cuprate physics. So once you get the disorders included, usually that you push into the more of this non-mature changes rather than linear changes. But starting with the nodal depth things to create the linear slopes in the superfluid stiffness is rather difficult. So it's usually kind of worked the other way around. Can I just think about the in-gap state of the superconductors? I think that's a part I'm not sure. Yeah. Maybe I should kind of discuss with you. I think that, yeah, I haven't considered that part, but yeah, okay, yeah. But I know that usually in the superconducting, the cuprate community, usually when you induce the disorder there, T becomes, T linear becomes T to the some power of the alpha thing. So I think, yeah.
So I guess there is no way to measure like thermal conductivity in this kind of samples, because there was this paper by Patrick Lee which also showed that the thermal conductivity only depends on the ratio of VF over V delta. So that would be
there is a way. I think Dimitri mentioned about that. There is a way that one can do that. It's a little bit more involved experiments. It can be done.
But in the superconducting phases?
Well, in the superconducting phases, especially if it is nodal and the finite excitations are always expected, I would say that why not? right? In principle. But it's in principle, right? Experimental is in principle, but it requires time. So how much time? That's the question. Yeah.
Thank you for the nice talk. And my question is, I don't know if it's a question or more of a comment. It's related to her question. So let me start with the fact that in general, the superfluid stiffness and the superfluid densities are the same in homogeneous samples, in homogeneous systems, but conceptually speaking, they're not the same. One is the number of carriers that you have, and the other one is the energy you need to twist the phase of the... And in particular, in BKT physics, the smoking gun of a BKT transition is a clear jump of the superfluid stiffness with the critical line to T over pi.
Yes, yeah.
And if you show, please, the data of the superfluid stiffness measured by the kinetic inductance, and if you plot the critical line, I really don't see this clear jump.
That's right.
So I'm more prone to follow this precorrelative path proposal that you mentioned, and in general, that kind of shape, at least in my experience, is more likely to be a signature of filamentary superconductivity, of having some sort of homogeneous superconducting condensate. And this is also related to nonlinear IV characteristics, because one can show that nonlinear IV characteristics can also come directly from having an inhomogeneous system, not really from the unbinding of vertex anti-vertex pairs. So within this scenario, and of course this is independent from the pairing mechanism and from S wave, D wave, or whatever wave you might have in the system. Of course, those are two different topics.
I think that's a kind of really fair point. Indeed, I think therefore that including the Q plate where the superfluid stiffness linearly decreases temperature never be considered as a smoking gun, right? So in the same way that I would not say that this is smoking gun. The one good point about this BKT, that indeed if it is a superfluid stiffness at the BKT trend, below the BKT transition temperatures, you expect kind of rather strong drops of this jump of this thing. That's related with our experimental limits. As I mentioned, I already made my escape route. When you go to the high enough temperature, when sample resistance start kind of about to rise, that's where I cannot get this really good estimation of the superfluid stiffness or the kinetic inductance measurement. So,
but you also have this shape at low temperature, right, of the superfluid stiffness, which is also, I mean, the critical temperature is not really defined as, I mean, it is defined, that's the critical point of the transition, but in general, that comes from the fact that you have vortex, anti-vortex, which starts to renormalize that. So if you would, I don't know, it should be clear if you can also plot on that.
So I just show that this is a linear plot, and I can draw the linear line.
No, I mean the 2t over pi, which would be something like that, right?
So you're asking...
And then you should see really a drop. So and if you look at that, you don't see a drop. You see a plateau and then a drop again.
Right. So that I'm just kind of telling you that this part is less believable. Right? So that's kind of something that I mentioned, that our experimental technique, because of finite contact resistance and resist part is getting there, we cannot just resolve the wear onto the distribution. So that's kind of the weaker part of our data, that I cannot just anything discuss about what is really happening there. And disorder is another thing that interesting. So I don't know whether I have this one. At least there are some calculation, I guess, this guy. Right? So people did, I think, this paper, if you just look at there, then also different S wave, D wave, and P wave, and they just kind of put this clean and dirty. At least conclusions I'm getting from this calculation is that I can make it anything more sloped. If I get clean, if I get the kind of dirty, then I get kind of more flat, right? So I'm getting the slope, the clear slope in the experimental data. So the minimum thing that I can say that is, well, it sounds like unless there's somebody that cook up this theory that I can get the sloped behaviors, if I just consider certain type of the disorder, I will stick with my simple interpretations. Speaking about the disorder, I think that's another interesting part. I already showed that this is not only one sample that show you that that samples that kind of rather scattered, right? So let me just kind of show you on these plots here. So this is the data we just get. Of course, we got the hero ranges that we analyze with the linear slope. And when you get this kind of different sample, their behavior is very different, right? Their disorder contents kind of rather different. But one thing that I can state is that if I just choose the samples, and any sample that I'm clearly seeing that there is a lesser disorder in the phase diagram, I always do see the linear sloping down. Mm-hmm. If I go to the disorder regions of the many sample, I see that it's not necessarily sloping down. It was rather flat, right? So at least I can see that throughout the sample, the correlation between the disorder and then these zero DT slopes.
When, I'm sorry. Yeah.
We can talk about the lunch. Yeah. Yeah. Okay.